All right, chemistry kids, I have assigned you a few different sets of problems. So due tomorrow is the ST6 grams to grams stoichiometry 1 set. So the ST6 is what it should say at the top. On the Google Classroom assignment, you would have seen a few different ones. I think ST6, ST7, ST8, and ST9 are problems that I have set up for us to do in the coming days, but just ST6 is due tomorrow. So under ST6, you're going to have problem 1, 2, 3, 4, and 5. Problem 1 has 5 parts. So if you look at problem 1 here, I'm going to kind of minimize my other ones so you can kind of get a picture here of what we're looking at. Under problem 1, there are an A through E part. Now, each one of those is just a scaffolded approach for a large stoic calculation that we've been doing. So let's start very first step by writing out our balanced chemical equation, because these ones are very nice to us, and start off with the balanced chemical equation. So we've got CH4, which hopefully we know by now is methane, and oxygen gas. So at a quick glance, starting next chapter, you'll be able to tell right away that this is what's called a combustion reaction. And we can tell that because we have a hydrocarbon, this guy, in the presence of oxygen, and it will always produce carbon dioxide gas and H2O. Methane is the most simple, clean burning version that we're going to look at here right now because it's just 1 part carbon with 4 parts hydrogen. So obviously it would produce less carbon if it started with less. So if you think about this in terms of what combustion is a burning of something. And what do you know that needs to happen for fire to happen? For something to catch fire and burn, it needs oxygen, like flame needs oxygen, and it needs a fuel source. So this is our fuel source, a hydrocarbon. This is our presence of oxygen. And if you think about what is hazardous for the environment in terms of vehicles, because they are combustion engines, it's because they produce carbon dioxide. So we will get into this more next chapter, but just a very broad overview of what this equation is doing here for us. So we are going to start by whatever they've given us. So my number 1 says, suppose that 448 grams. Now because you don't have paid access to this, it will change that number every time, and each one of you is going to have a different number to start with. So if I'm starting with 448 grams of methane, and I want to get to the moles of methane, anytime you are going from grams to moles, you know you need to use the molar mass. Okay, molar mass is always simply the mass of 1 mole of any substance. So in 1 mole of methane, what is the mass? So what you're going to do is you're going to look at carbon on your periodic table and see that it is 12.011. 12.011. And then you're going to find hydrogen on your periodic table and see that it's 1.008, but there's 4 of them. And you're going to end up with a mass of 16.043 grams. All right, so remember, this is that equality statement that I'm going to use called my molar mass, and I know it's what's going to get me from mass to moles of methane. Because I start with grams of methane, I know I need grams of methane on bottom. I have 16.043 grams of methane. I'm going to try to rewrite that with the finer points so you can see it better. So 16.043. Now that's going to be the same for all of us because that is the molar mass of methane. So if you are going from mass to moles of methane or moles to mass, you will always use this equality statement because grams of methane cross off. Maybe I should start using this as my cross off tool. Maybe I'll grab a different color so it's a little bit more obvious. Oop. All right, so that crosses off and that crosses off. So now what I'm left with is moles of methane, and that's what I wanted to get to. So I'm to the point of getting my answer, but I have to type it into my calculator. So my number again was 448 grams, and I'm going to divide it by my molar mass, which is 16.043 grams. And my final answer is going to be 27.9249, yada yada. I only have 3 sig figs because I'm always going to use just my given quantity, and I had 448. So my number rounded to 3 sig figs is 27.9. This thing is really flexible with sig figs because I did not get paid access for you guys, so it's going to be pretty flexible. So I probably could have put in 28 and it probably still would have accepted it. I did type in an incorrect answer here for you to see very quick that 31.9, when I typed that in, it came up and said red X. It doesn't, it'll be green with a check mark next to it when you do it correctly. And each time you'll be able to see what numbers you've put if you just click on your attempts. All right, if you're having a hard time with your ads, go ahead and exit out of the ad and then try hit submit. The delay is our spam blocker interfering with all of the ads and not letting them all pop up on your screen. All right, next it says, how many moles of carbon dioxide are produced? So I started with moles of methane, and I want to get to moles of carbon dioxide right there. So I'm going to look at the molar ratio because there is nothing here. I know that it's a 1 and a 1 technically. All right, so for my conversion here, I'm still looking at 448 grams like I started with, and I'm still going to carbon. I can go to carbon dioxide actually from where I'm at right now, because my first step would have to be getting out of grams of methane, so I can just use the work I've already done and add to it. So meaning now I'm in moles of methane. To get from moles of methane to moles of CO2, I'm going to say that for every 1 mole of methane, I have 1 mole of carbon dioxide. And because I had methane on top, I have to have methane on bottom. So that crosses off, and it's equal to 1 mole of carbon dioxide. Now this is called the molar ratio. So I'm going to delete this. This is molar ratio. And it is always found by looking at the coefficients in the balanced equation. Okay, that balanced chemical equation, those coefficients tell me what I can use. And if there is no coefficient, it means 1. All right. So I have gone from grams of methane to moles of methane to moles of carbon dioxide, and that's what I wanted to be in. Because it's a 1-to-1 ratio here, I can actually say that the number is not going to change. So I have the exact same number that I had in the previous problem, 27.9 moles of carbon dioxide. All right, next it asks me for the mass of carbon dioxide produced by 448 grams of methane. Now, I'm in the same starting quantity as my first problem. I'm still in 448 grams here of methane. Let me erase some of this stuff so you can see that this a little bit clearly. So I can still use this because this still would be my first step. All right, I still need to go between these guys here. All right, so because I'm still starting with this 448 grams of methane, I still need to get out of methane to get to carbon dioxide. And so then I go from moles of methane here, because anytime you're in moles, that's how you're going to convert to any other substance in the equation. Now I go from moles of methane to moles of carbon dioxide. So now I know how much carbon dioxide it is in terms of moles, but I have to get from moles of carbon dioxide to mass, because that's what they're asking for, the mass of CO2. So I'm going to add another step here. It's going to be like rainbow colors here. So so far, grams of methane crossed off. Uh, there's a G there. Moles of methane crossed off. Now I need 1 mole of carbon dioxide on bottom, and I need the grams of carbon dioxide on top. So I'm going to look to my periodic table and realize that oxygen is 15.999, and there's 2 of them. So that comes to 31.998 grams, plus carbon's 12.011, and I get a mass of 44.009 grams of carbon dioxide. My moles of carbon dioxide cross off. I'm in grams of carbon dioxide. Now I'm going to just do the math because I'm in the unit I want to be in, so 448 divided by 16.043. The ones aren't going to change a thing, times 44.009. My number comes out to 1,228.949,199. I'm only given still the 3 sig figs initially. Every other value I've used is called an accepted value and does not contribute to sig figs. So if I round this to the correct number of sig figs, here's a good test for this program if it's going to accept it on me here. So 1,228.9. I'm going to just give you an estimated, and if I have 3, I'm going to look to the right, so I get 1,230, and that is grams of CO2. It's not likely to accept scientific notation here, so let's just type it in like this, so 1,230, and it marked it right. Okay, so next it says how many moles of H2O were produced. We are starting with the same given, so I could literally start here, I could start here, here, or here. All of these are true statements for 448 grams of methane. I think preferably for most of you, it'd probably be to start fresh, so I am going to just do another one. Okay, so I'm going to, come on, used my wrong tool here. I'm just going to start with a new conversion here. Let's go with my pink again. So if I start with 448 grams of methane, still we have the same amount of fuel available. And I want to get to moles of H2O and then mass of H2O. So let's go moles H2O and mass H2O. That's the next one. All right, so step 1 would be to get out of the mass of methane. I can't do anything with that, so I know if I have 1 mole of methane, CH4. Same as up here, I've got 16.043 grams of methane. Now grams of methane cross off and I'm in moles of methane. Now I need to get from methane to H2O. Now there are 2 parts H2O for every 1 part of methane. Again, we get that by the coefficients. If there is no coefficient or number in front of that compound, that tells us there's only 1. So every time I have 1 mole of methane, I'm going to have 2 moles of H2O. Okay, because there's a 2 here and nothing here, so that's a 1. All right, now moles of methane cross off, and I'm in moles of H2O. So that was the first part. How many moles of H2O are produced? So I'm going to take 448 divided by 16.043 and then times 2. And that tells me that here I'm going to have, with 3 sig figs, 55.8 moles of H2O. Now I wrote it down here because even though that is this answer, hopefully, if I didn't type something incorrectly here, 55.8, then I can just go now, which the next problem is asking me the mass of H2O. If I know 1 mole of H2O has, okay, 15.999 from oxygen, plus 2 hydrogens, 1.008 times 2, is going to give me 18.015 grams H2O. Moles of H2O cross off, and I'm in grams, which is what this one's looking for. So I'll take that 448 divided by 16.043 times 2 times 18.015. I get 1006, but if I round that to 3 sig figs, I get 110 grams of H2O. Now, preferably, I wish we could put in scientific notation. It is the one downside to this, but I do like that it's going to give you immediate feedback for each of your steps, so you can see at a quick glance how it's going. So we're going to have to type this guy in, but hopefully we know scientific notation well. On your quiz, you will need to do it. All right, so we got 1, 0, 1, 0. Cross our fingers, I didn't mess it up. Oh, good. All right. So next problem. See, there isn't as many parts for the next one, so those of you that were panicking, it's not that bad. And thinking about these things when you don't have all your buddies around you will probably be advantageous to your grade. All right, so we're going to start with the balanced chemical equation. I'm just going to write it out so I've got it in front of me. We're going to have 1 part calcium and 2 parts H2O. If you remember anything about the periodic table, you might remember that calcium is going to react violently in water, and it's actually going to form a very unique substance and release gas. By unique, I mean it's just going to form a good base here, which is calcium hydroxide. How fun is that? All right, so we've got H2 gas and calcium hydroxide from calcium, which would be a solid, put in water. Okay, so now we're going to do the stoich they want. They said these people have 80 grams of calcium in their test tube. So 80.0 grams of calcium. All right. When the reaction was complete, the calcium was no longer present. So that means they used all of their calcium. Calculate the moles of calcium that were reacted. So how many moles of calcium are there in 80 grams? In 1 mole of calcium, we know the mass is 40.078 grams of calcium. So grams of calcium cross off, and I'm in moles of calcium, which is what this first problem wants me to do. So I'm just going to type it in my calculator here. 80 divided by 40.078, and we're going to get about 2, which you probably could have seen right off the bat. But I wanted to check how sig figs are going to look here. If we have 3 sig figs, yep, it would still round to 2.00. I want to show you the last time I actually used sig figs, it literally took away my zeros. Yep, it did it again. But it would be 3 sig figs, because the only thing that matters was you're given having 3 of 80.0, or whatever your mass that they gave you to start with was. Now B says determine the moles of H2O that would react with 80 grams of calcium. So I'm still starting with calcium. Now they want you to go from calcium to water. So how much water did it take for this reaction to complete? Now this is an example of stoich, pretty similar to what we'll be doing, except you're going to predict an outcome and figure out how much you need to make it work as well. So we know that in order to relate calcium to H2O, we're just going to look at the coefficients. So if we have 1 part calcium, we're going to have 2 parts H2O. It's just those coefficients. So 1 mole of calcium is going to require 2 moles of H2O. Moles of H2O cross off. I'm in moles of moles of calcium cross off, and I'm in moles of H2O. So I'm actually just going to take my previous number times 2, which will actually give me about 4. Okay, so I just took that times 2. Now I'm in moles of H2O, and this last problem says determine the mass of H2O required still with the same initial mass. So if I have 1 mole of H2O, I'm going to have about 18.015 grams of H2O. So I'm going to take that 4 approximately. So I've actually got 3.9922 yada yada on my calculator here. And I'm going to take it times 18.015, and I get about 71.92. And I have 3 sig figs to work with, so I'm going to say 72.0 grams of H2O. Again, it took away my sig fig, but hopefully you know how to do it. All right, this next problem isn't much more challenging at all. It's again another combustion reaction. So just like before, let's start by writing our balanced chemical equation. So we have C3H8, again, that's our hydrocarbon, used as a fuel source in the presence of oxygen, the O2. And it's always going to yield carbon dioxide and water. And if it's not an efficient burn, it'll actually release other stuff. Oop, I just did carbon trioxide. How fun would that be? All right, and H2O. Now our coefficients will be a 1, 5, 3, 4. 1, 5, 3, 4. Okay, how many moles of the hydrocarbon did he burn if he started? So just like before, my mass may be different than yours. It in fact should be 528 grams of C3H8 is what I'm starting with. And I want to get 2 moles of this. So anytime you want to get mass to moles, you're going to use the molar mass. So 1 mole of C3H8 on your calculator. You probably have gotten carbon and hydrogen memorized by now. 12.011 times 3 plus 1.008 times 8. Now I get a molar mass of 44.097 grams C3H8. All right, our grams crossed off and we're in moles of C3H8. So I'm going to take 528 divided by that molar mass. And I get 11.9736, yada yada. But if I was only given 3 sig figs, I'm going to round it to 12.0 moles. And remember, if we're naming this with molecular nomenclature, it would be tricarbon, and then you'd have to use the prefix for 8, which we don't actually use very often, but it's just octa. But because it's, so tricarbon octahydride would be the molecular name, but the hydrocarbons are always going to have a simplified name as well. All right, submit that. Now, how many moles of O2 are going to react with it? Okay, so moles of O2 this time. So now I'm going to go same mass, 528 grams. Again, you don't have to put the of if you don't want to. 1 mole C3H8. Oh, I don't know why I'm doing this again. Silly goose. I'm just going to go up and work on the previous problem. Because I can just add on to this because I'm into moles of that hydrocarbon. And if I want to go from moles of the hydrocarbon to moles of the oxygen required to make this happen, I can just say because there is no prefix, that's a 1, and there's a 5 here. So it is 1 mole of C3H8 for 5 moles of O2. All right, so now I'm in moles of O2, which is what I wanted to be in. So I'm going to take 528 divided by 44.097 times 5. And my calculator says 59.868. And I have 3 sig figs, so let's go 59.9. What, sweetie? You what? You're still hungry and you ate a full apple? Is there anything else over there you can have for a snack? You want to go look in the fridge? There's yogurt, I think. C says what mass of O2 is required for this. Again, same mass to start with. So I can just erase this guy and add another conversion factor here. Yep. And we want to know the mass of oxygen gas, and I already am in moles of oxygen gas. So I know in 1 mole of O2, this is a problem you guys have struggled with a few times because it's O2, it's a molecule. We have to take that 15.999 when we look at oxygen, but do 2 of them. So my mass comes out to 31.998 grams of O2. Okay, that's a problem I could envision you guys making on that one. So in my calculator, I'm going to type 528 divided by 44.097 times 5 times 31.998. And I'm going to get 1915.6 and on here, but I only have 3 sig figs. So I'm going to go 1,920. All right, how many moles of carbon dioxide were produced? This is a good thing to be able to calculate. How much gas is this actually putting into the environment? How much hazardous, I wouldn't say hazardous, but dangerous. How about that? Dangerous to our environment gas here. So we are already in grams of O2. So you can either just convert from here on or come back to anywhere where there's moles and go on. Because we were starting with 528 grams of our hydrocarbon, we definitely would have needed this to be our first conversion factor. So if I'm going from now this to carbon dioxide instead, I can just start here and say that if I have 1 mole of C3H8, I'm going to have 3 moles of CO2. Okay, the first one said how many moles, so this is all I needed. I'm in moles of CO2. My moles of hydrocarbon crossed off. So 528 divided by 44.097 times 3. With 3 sig figs, I get 35.9. 35.9. All right, and what mass of CO2? So now moles to mass, just like always, is your molar mass. So in 1 mole of CO2, I have 15.999 times 2 plus 12.011, and I get 44.009 grams CO2. All right, now I'm going to just type this into my calculator. All right, 528 divided by 44.097 times 3 times 44.009. And I get 1,581-ish, but with 3 sig figs, it comes to 1,580. 1,580 with 3 sig figs. All right. Now notice as I finish these sections up top, it's going to tell you that I've now completed problems 1, 2, and 3. I would take a screenshot before you exit out of this because it's going to refresh. And then when you jump back in, you can just start with whichever one you ended with. So if I came back, I would just start with 4. Remember, a screenshot on your Chromebooks is Control-Shift. If you want to just do a screen grab, it's the Windows key. If you want to just take a picture with your phone, just make sure it's clear enough that I can actually see it. All right. So ST6 Q4, consider the balanced chemical equation. All right, we've got nitrogen gas and hydrogen gas making some ammonia. I'm going to just set up a couple of them first. This video is getting quite long. So nitrogen gas N2 plus 3H2 yields 2 parts NH3. All right, so synthesis of ammonia means you're putting things together and it's making just this one thing, ammonia. It says that you're trying to make 136 grams of ammonia. All right, how many moles of ammonia are produced? So we know if we have 1 mole of ammonia, we're going to take nitrogen's mass in the periodic table is 14.007 plus hydrogen 1.008, and there's 3 of them, and I get a mass of 17.031 grams NH3. Grams of NH3 cross off, and I'm in moles, and that's what I wanted to get to, so 136. Again, your number's going to be different, and that gives me about 8. I was given 3 sig figs though, so I'm going to do it, even though one of these times is probably going to not like it. 7.99 is what I get. Okay, how many moles of nitrogen gas must you have for this to work? So we're just going to use the molar ratio to get for moles of ammonia. There's 2 moles of ammonia for every 1 mole of nitrogen gas. Again, you're just pulling that coefficient. Okay, so I'm just going to take my previous number and divide that by 2. So I get about 4 moles of nitrogen gas are needed. Okay, now what mass of nitrogen must you need? Now you're just going to go for moles of nitrogen. So in 1 mole of nitrogen gas, N2, I'm going to take 14.0007 times 2, and it gives me 28.014, 28.014 grams nitrogen gas. That crosses off, that crosses off. So then I'm going to take my previous answer and just take it times 28.014. And I'm going to get, with 3 sig figs, 112 grams. All right, how many moles of hydrogen must react? So you have 2 things you could do. Well, multiple things actually. You could start with any one of these quantities. You could have started here, you can start here, you can start here, or here. So I would just choose the one that you think is going to be the most sensible to you. So if you just want to start at 136 again, that's just fine. But I am going to start by taking this off, because I know my first step is going to be to do this regardless, because I have to take that mass that I've been given and get out of that mass of ammonia and get into moles in order to jump between anything. Okay, the only thing we can use is the SI base unit for a substance when we're converting between different things within a chemical equation. So I want to get to H2 this time. So I'm starting here and I want to go here now. So I know when I have 2 moles of NH3, I'm actually going to have 3 moles of H2. So I'm going to take 136 divided by 17.031 times 3 divided by 2. And I'm going to get about 12. Okay, but to 3 sig figs, it gives me 12.0. It's going to delete my 0, but... All right, now what mass? Now I can just keep going because I'm in moles of the substance. Now I can just go, well, that's off. That's off. And I know if I have 1 mole of H2, I have 2.016 grams of H2. It's just your mass on your periodic table, 1.008 times 2. So I'm going to take my previous answer and I'm going to take that times 2. So 12 times 2 approximately is going to give me approximately 24.0. And there it is. All right, that was ST6 question 4. I might as well just commit here and finish this off for you. Okay, so the very last problem. What time is it? The very last problem is aluminum. Ooh, aluminum being oxidized. Okay, 4Al plus 3O2 is going to yield 2 parts of Al2O3. So we got coefficients of 4, 3, 2, aluminum by itself, oxygen gas yielding aluminum oxide. All right, we're starting with a 135 gram sample. I'm going to move a little faster this time, guys, and kind of shoot through it, and then I'll come back and do the calcs. All right, so 135 grams of aluminum is going to go through this oxidation. I know I need to get out of aluminum, so 1 mole of aluminum, looking at my periodic table, is going to give me 26.982 grams of aluminum. My first problem is going to, so that would have been A. Now B is how many moles of Al2? So I know when I have 4 moles of aluminum, because that coefficient, I'm actually going to have 2 moles of aluminum oxide. All right, so that was B. How many aluminums to how much aluminum oxide? Now what mass of aluminum oxide? To go moles of aluminum oxide, I know in 1 mole of aluminum oxide, Al2O3 So I'm going to take that mass of aluminum, the 26.982 times 2 plus 15.999 times 3, and I get a mass of 101.961 grams Al2O3. All right, that would have been the mass of aluminum oxide for C. Okay, so I'm going to plug these numbers in and get my numbers here. So 135 divided by 26.982. So this one should be, with 3 sig figs, 5.00. All right, how many moles of aluminum oxide are produced? Now I'm going to take that times 2 divided by 4, and I'm going to get 2.50. Now I'm going to take that times 101.961, and I get a mass for my aluminum oxide of approximately 255 grams. All right, now how many moles of O2 are going to react with the same mass? So again, I could take any one of these, but if I'm going to oxygen, so let's just change our colors here. Now we're going here. So I think it's going to be easiest just to go from here to here and just erase this chunk here on us, because then we can just say, all right, what's my molar ratio to go from aluminum? So 4 moles of aluminum still, but I'm going to oxygen this time, so it's 3 moles of oxygen. So that first question said how many moles of oxygen will react. So I'm going to take 135 divided by 26.982, and I get about 5, but with 3 sig figs, it's going to be 5.00. Oh, what did I do wrong? Aluminum, 135 grams of aluminum. Oh, shoot, I only did one. I stopped too early, sorry. It's 135 divided by 26.982 times 3 divided by 4. Let's get ahead of myself here, or behind, I suppose. 3.75. 3.75. All right, now mass. So now we're going to go from 1 mole of O2 is 31.998 grams of O2. Again, it's 15.999 grams of oxygen times 2. So I'm going to take that 3.75 that I've got on my calculator still times 31.998, and I'm going to get 120 approximately grams. All right, now none of my answers are probably going to line up exactly with yours, but the process is the same. Use your numbers, do your work. Now see how when I come back up here, it shows me that I got 100% because I did all of the problems and I ended up getting them right. I do believe there's a certain point where it'll dock you points if you've tried too many times. All right, that is the it.